3 days ago, NASA published something that barely made the news, and it should have made all of it. On April 15, 2026, scientists published a paper in the Astrophysical Journal describing what a NASA telescope just mapped inside our own galaxy. Frozen regions of space so enormous, stretching more than 600 light-years across, that scientists had to invent a phrase to describe them. They called them interstellar glaciers, not metaphorically, not poetically. That is the actual term the scientist who built the telescope used in the official NASA announcement. Interstellar glaciers. And what those glaciers are made of is not ice in the way we usually think of ice. It is water, carbon dioxide, carbon monoxide, frozen onto the surfaces of particles of cosmic dust, sitting silently in the nurseries where new stars and new solar systems are being born. The scientists said something else too. Something that stopped me when I read it. They said we are looking at a map of material that could rain on nascent planets and potentially support future life. We mapped where life might come from. That is what happened 3 days ago. If that is the kind of content you come here for, hit subscribe right now. It takes 2 seconds and you will not miss what comes next. Now let me explain exactly what was found, how it was found, why it matters, and what it might mean for one of the biggest unanswered questions in the history of science. Let's start with the tool that made this discovery possible. Because without understanding what SphereX is and why it is different from every telescope that came before it, you cannot fully appreciate what just happened. SphereX launched on March 11, 2025. Its full name is the Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer. NASA is not modest with acronyms. But here is what makes SphereX genuinely unusual. Most space telescopes are designed to zoom in. Hubble, James Webb, Chandra. These are precision instruments that take extraordinarily detailed images of specific targets. You point them at something and they look very, very closely at that one thing. SphereX does the opposite. It is designed to look at everything. Its goal is to map the entire sky, not once, but 4 complete times. And it does this in 102 different colors simultaneously. Every one of those 102 colors is a different wavelength of infrared light. And each wavelength carries different information about what different molecules are doing in different parts of the universe. Think of it this way. If you look at a piece of paper with your eyes, it looks white. But if you look at it with an ultraviolet light, you might see markings invisible to the naked eye. Different wavelengths reveal different things about the same object. SphereX does this for the entire sky at once, in 102 different ultraviolet to infrared bands simultaneously, cataloging hundreds of millions of objects as it goes. By late 2025, SphereX had completed its first full all-sky infrared map, the first of 4. And the scientists analyzing that first map found something they did not fully expect. Not in one specific place they were looking at. Distributed across vast regions of the galaxy, in quantities and at scales that nobody had been able to see before. Ice. Enormous, ancient, cold, silent ice. So what exactly did they find and where? The discovery is concentrated in 2 regions of the Milky Way, Cygnus X and the North American Nebula. Both are located in the constellation of Cygnus, the Swan, and Cygnus X in particular is one of the most active and turbulent regions of star formation in our entire galaxy. It sits roughly 4,500 light-years from Earth. Inside Cygnus X and the North American Nebula are what astronomers call giant molecular clouds. These are exactly what they sound like, massive regions of gas and dust, held together by their own gravity, slowly cooling and condensing over millions of years. When clumps within these clouds become dense enough, they collapse under gravity, heat up, and ignite. A star is born. And usually, as that star forms, the leftover material in a spinning disk around it eventually coalesces into planets. Every star system in the galaxy, including our own sun, and every planet orbiting it, including Earth, began inside a molecular cloud like the ones in Cygnus X. What SphereX mapped, in unprecedented detail across regions spanning more than 600 light-years, is that these molecular clouds are not just clouds of gas and dust. They are full of frozen molecules, water ice, carbon dioxide ice, carbon monoxide ice, all of it coating the surfaces of tiny dust particles. particles no larger, according to the research, than the particles you would find in the smoke from a candle flame. Individual grains of dust, each one coated in a shell of frozen molecules. And there are so many of them, so densely packed across such vast regions of space, that SphereX could see the frozen material distributed across entire sections of molecular clouds simultaneously, like seeing the shape of a glacier from above rather than just spotting individual snowflakes. That is the scale of what was mapped. Not specks of ice, not localized pockets. Continuous frozen complexes spanning hundreds of light years. Whole regions of the galaxy where water and other molecules exist in frozen form, waiting. Now here is the discovery within the discovery. The thing that was actually surprising to the scientists themselves. Before SphereX, the way astronomers detected ice in space was straightforward. You find a bright star. The star's light shines outward in all directions like a spotlight. If there is ice between you and the star, that ice absorbs specific wavelengths of infrared light. You look at the spectrum of the starlight reaching your telescope, see which wavelengths are missing, and you know what molecules absorb them. The star does the work. But this only tells you about a thin column of space between you and that one star. It is useful but limited, like trying to understand the shape of a mountain by looking at a single cross-section. What SphereX found was completely different. Lead researcher Joseph Hora, an astronomer at the Center for Astrophysics at Harvard and Smithsonian, described it directly. He said, "We expected to detect these ices in front of individual bright stars, where the light from a star acts like a spotlight, revealing any ice in the space between us and that star. But this is something different." What SphereX was seeing was not spotlight illumination of individual ice columns. It was something that only becomes visible when you have an instrument capable of detecting very faint, diffuse background light coming from an entire galaxy plane at once. Along the galactic plane, where most of the stars, gas, and dust of the Milky Way are concentrated, there is enough combined background light shining through entire dust clouds that SphereX could see how the ice was distributed spatially across massive volumes of space. The difference is like the difference between shining a flashlight into a dark room and examining one patch of wall versus turning on the overhead lights and seeing the entire room at once. SphereX turned on the overhead lights for entire regions of the galaxy, and what it revealed in the images it produced is striking. When scientists mapped the water ice in Cygnus X and overlaid it on images of the dust in the same region, the water ice mapped exactly to the densest regions of dust. Perfectly. Precisely. The frozen water lived where the dust was thickest. This is not a coincidence. This is a confirmation of something scientists had theorized for decades but never been able to see at this scale. The theory is this. In the cold, dark interior of a molecular cloud, shielded from the ultraviolet radiation of nearby stars by the surrounding dust, molecules in space can freeze directly onto the surfaces of those tiny dust grains. The dust acts as both a substrate and a shield. Carbon and oxygen atoms drift through space. They land on a dust grain. They bond together in the cold, forming carbon monoxide. More atoms arrive. More molecules form. Water molecules, carbon dioxide molecules, other organic compounds, all condensing slowly onto the surface of particles smaller than the smoke from a candle in the cold, dark interior of a cloud over millions of years. The dust shields these molecules from the ultraviolet radiation of newborn stars nearby, radiation that would otherwise break the molecular bonds and destroy the ice. Inside the dense regions, protected by the dust, the ice survives. SphereX confirmed this mechanism at a scale nobody could see before. The densest ice is exactly where the densest dust is. The dust and the ice are not just correlated, they are functionally inseparable. The dust is the ice's protection. The ice is the dust's passenger. And what is riding on those passengers matters enormously. Let's talk about what ice in space actually means, because this is where the discovery connects to something much larger than chemistry. The most common ice found in these molecular clouds is water ice, regular H2O, frozen. This is important for reasons that might seem obvious but are actually deeply scientifically contested. Earth has oceans, enormous, life-sustaining oceans covering 71% of the surface. Liquid water in quantities almost impossible to comprehend. And for a long time, the origin of all that water was a major unsolved problem in planetary science. The early Earth, as it formed from material collapsing around the young sun, would have been hot, very hot. Hot enough to have driven off most volatile molecules, including water, into space before the planet fully solidified. So where did all the water come from? The leading answer involves delivery from outside. Comets, asteroids, and meteoroids carrying water ice that formed in the cold regions of the early solar system, crashing into the young Earth over millions of years and depositing their frozen cargo. The water raining down. The oceans accumulating impact by impact. If that theory is correct, then the water in your oceans, the water in your blood, in every cell of your body, came from ice that formed in a molecular cloud like the one Spherex just mapped. Ice that coated the surfaces of tiny dust particles over millions of years, survived inside the cloud, got incorporated into comets and asteroids as the solar system formed, and was eventually delivered to a young planet at just the right distance from its star to keep that water liquid. The interstellar glaciers that Spherex mapped are the source, the origin point of the process that begins with frozen molecules on tiny particles of cosmic dust and ends with oceans. Phil Korngut, the instrument scientist for Spherex at Caltech, put it in the clearest possible terms. These vast frozen complexes are like interstellar glaciers that could deliver a massive water supply to new solar systems that will be born in the region. It is a profound idea, he said, that we are looking at a map of material that could rain on nascent planets and potentially support future life. That sentence deserves to sit with you for a moment. A map of material that could rain on nascent planets and potentially support future life. Not on planets we are trying to find. Not on distant exoplanets we can barely detect. On planets that have not been born yet. Planets that will form inside Cygnus X and the North American Nebula over the next millions of years. From material that currently exists frozen in those molecular clouds, mapped for the first time by a telescope that has been operational for barely a year. There is something else in this discovery that makes it scientifically significant beyond just the water ice. Spherex did not just find water, it found carbon dioxide and carbon monoxide as well, frozen in the same clouds. And what was remarkable is that different ices behave differently in the same environment. Water ice and carbon dioxide ice do not respond to environmental factors in the same way. The amount of each ice changes across different parts of the molecular cloud based on different conditions. Temperature gradients, radiation levels, density variations. Gary Melnick, an astronomer at the Center for Astrophysics at Harvard and Smithsonian, who leads the Interstellar Ices Project, explained why this matters. He said, "We can investigate the environmental factors that contribute to different ice formation rates across large areas of interstellar space." The Spherex mission's big picture view provides valuable new information you cannot get when zooming in on a small region. And within this broad perspective, Spherex can do something that ground-based observatories fundamentally cannot. It can detect varying amounts of water and carbon dioxide simultaneously across the sky, allowing scientists to compare how the two respond to different conditions over enormous scales. This is important because it allows scientists to test specific models of how ice chemistry works in the interstellar medium. Not just detecting that ice is there, but understanding the conditions under which different molecules form, survive, and eventually get incorporated into new star systems. That understanding feeds directly into our models of how planetary systems like our own develop the chemical ingredients for life. Now let's zoom out one more time, because this discovery needs the context of what Spherex still has ahead of it. What was announced on April 15, 2026, is based on the first of 4 planned all-sky scans. Spherex has only been operating for just over a year. The data being analyzed right now represents 1/4 of the total science this mission is designed to produce. 3 more complete maps of the entire sky are coming. Each one will add to and refine what the first found. The coverage will extend beyond Cygnus X and the North American Nebula. Scientists will be able to compare the distribution of ice across different molecular clouds with different characteristics, different ages, different radiation environments, different density profiles. They will be able to map the chemistry of star-forming regions across vast sections of the galaxy in ways that have never been possible before. The study authors noted that even within the Cygnus X data, there are molecular clouds still being explored. The big picture view that SphereX provides is catching things that telescopes focused on smaller regions simply cannot see. And those things, the large-scale patterns of how ice is distributed, how it correlates with dust density, how it varies between regions, are exactly the kind of information that tells you not just what is there, but how it got there. 3 more scans, 3 more passes over the entire sky, 3 more opportunities to refine, expand, and deepen the picture that this first announcement has started to draw. The question that this discovery is answering, or beginning to answer, is one of the oldest and most profound in science. Not just where did Earth's water come from, but whether the process that gave Earth water, and through water gave Earth life, is common. Whether molecular clouds throughout the galaxy are seeding new solar systems with the ingredients of life as a regular feature of how star formation works. Whether what happened to Earth is a coincidence or a pattern. SphereX is mapping that answer, one infrared color at a time, across the entire sky, in 102 wavelengths simultaneously. And 3 days ago, the first chapter of that answer was published in the Astrophysical Journal. Interstellar Glaciers, hundreds of light years across, sitting in the nurseries of new worlds, waiting to rain down. If this video gave you something real, and I genuinely hope it did, please do 2 things. Hit the like button. It is the simplest way to tell me this kind of content is worth making, and it helps more people find it. And if you know someone who would sit up straight reading about water from space and frozen galaxies and the origin of life, share this with them. They deserve to know this happened. Subscribe if you are not already, because SphereX still has 3 all-sky maps to complete. And when the next major discovery comes out of this mission, I will be here covering it exactly like this. The universe just got a little less mysterious and a little more extraordinary. Stay curious.